What is the strongest intermolecular force for that one? For the first one, so for HCl. So looking back at these, so remember, these are the ones that are actually in order. London forces is when you have only carbons and hydrogen. Dipole is if there's just one nitrogen, oxygen, fluorine, or chlorine. Hydrogen bonding is if you have an oxygen or a nitrogen with a hydrogen attached. If you have any kind of salt and water, that's ion dipole. And then if it's a salt, then that would be the ionics. Remember, you can recognize salts or metals and nonmetals. So those are the 5. So looking at HCl. It'd be dipole. Dipole, because this one's going to be polar. Because of that chlorine, but it can't hydrogen bond. So the strongest attractive force would be a dipole. Dipole attraction. What about this one here? Yep, this one's London because it's nothing but carbons and hydrogen, right? So it's CH3, CH2, CH, CH3. So nothing but carbons and hydrogen. So that's a London force, the weakest of all of them. So then what about this one? You know it can't be London because you see there's oxygens. It's hydrogen bonds because of this OH, right? So that double bond oxygen is going to add that dipole factor into play. But because there's an OH, if you see a nitrogen with the hydrogen or an oxygen with the hydrogen, then you know that this can hydrogen bond. What about MgO? Yep, it's ionic because it's a salt. It's a metal and a non-metal, so that makes this one an ionic. Strongest of all of them. Looking at this, so looking at this, you should go, oh, that's glucose because that's a sugar. It's an aldohexose. What would you say is the strongest intermolecular force? Lots of hydrogen bonding. See all of those OHs? So everywhere that you have an OH, those can always hydrogen bond. So if you see OH or if you see NH in a molecule, then those are the hydrogen bonding characters. And then the last one, CaCl2 and H2O. This one's ion dipole. It's just a salt dissolving in water. Okay, so I gave you a couple of examples of those ones. I just wanted to go back and make sure that we did one more. Don't kick me off. Meh. Because we're going to go ahead and start chapter 8. So I think we should be able to cover the majority of chapter 8. Hopefully start some of the math part of it and then finish the math part and all the way through transport processes, which is at the end of chapter 8. We should be able to finish all of that by Monday night. So then I'll give you your take-home exam. So I'm just going to make it over the chapter 7 and 8. We will start chapter 9 on Wednesday, but it won't be on this. And that way it's sort of like another division, a divider there. And I think we should be able to throw chapter 9 stuff into exam 5. Okay, so chapter 8 is all about solutions. So remember that solutions are mixtures. So a solution, this is a mixture. And this chapter really just kind of defines the characteristics of, well, when you have a mixture, you have more than one thing physically combined. Well, the thing that is found in highest concentration is the solvent. It is the highest concentration, the greatest percent. That is always going to be the solvent. I always think of it as the dissolver. So it's what dissolves other things. So again, when you think about like coffee, so coffee is a mixture. Well, coffee, it might have cream in it. And cream, remember, has some fats. It has some proteins. But then it might also have sugar. It also has all of the caffeine, the flavorings, the colors. So all of the coffee, like pigments. So there's a whole lot in this mixture. Coffee flavors. But none of these exist in as high a concentration as water. Okay, the water that's used to dissolve all the pigments, all the flavors and colors of the coffee. There's water even in the cream. So water would be the solvent. All those other things are solutes. So solutes are always found in lower concentration. They're always a smaller percentage. I always think of solutes. They are what get dissolved. So in that example, I have a whole lot. But I mean, even if you're just talking about salt water, where you just take a sample of salt, put the little granules of salt in water, stir it up. The salt completely dissolves. You can't see it, but the salt is in lower concentration than the water. So the salt is typically going to be your solute. The water is the solvent. Okay, so these are just examples in mixtures, but being able to identify what's the solute, what's the solvent, whether you're talking about a solid dissolved in a liquid or two liquids being mixed together, whatever's in greatest concentration, that is always the solvent. So the solute, typically it can be varied. So I can add if you like really sweet coffee, you can add like 2-3 teaspoons of coffee, stir it up, or maybe you just like a half a teaspoon. So you can vary the amount of solute. As long as the amount of solute is less than the amount of solvent, then they still fit their categories. And they call it, if this completely dissolves, it's called a true solution. So a true solution is a type of mixture where we have very small particles. And I think of things like salt, like sugar, very small molecules. They are totally dissolved and they don't settle out. So this is not going to separate. You can alter how much of the solute you put in. You could put in a little, you could put in a lot. And they say that the intermolecular forces are similar. So they're either like both polar, both non-polar. You might have one that is salt dissolving in water, so they're both hydrophilic. That's a true solution. But there's two other kinds of solutions that you can have. You can also have what's called a colloid, and you can have a suspension. These are still called solutions, but they actually have a different characteristics. So colloids are where you have solute particles that are large. But they still have the same intermolecular force, so that keeps them mixed. So the solute particles are large particles. This can give sort of a thick texture to the solution, where it's just like salt water. It's very watery. Even just your coffee, it's real watery unless you start adding a whole lot of cream, because that's the colloid. So things that add, like I think of cream, I think of like gravy, Jell-O. Jell-O is where you have proteins dissolved in water and it makes it real thick. Gravy is when you boil starch, like what we did in that diffusion lab last week. So that starch, it was just starch boiled in water and it had kind of a thick texture to it. When you poured it, it was thicker than the salt was. These are examples of colloids. They're large, but they stay mixed. They don't settle out. But because they're large, they can give a thick texture. By definition, they say that these particles are usually 100 to 1,000 times bigger than the ones that you find in a true solution. But those are just examples of a food type that you've had that is actually a colloid. Now a suspension though, a suspension is where the particles are even bigger. So these really have huge solute particles. And typically with a suspension, the particles do not have the same intermolecular force as the solvent does. So what this will do is this will separate. It does not stay mixed. So different intermolecular forces. Suspensions are going to separate unless you mix them. So like an example of this is just dirt and water. Right? The particles of dirt are really big. But if I shake this up, it'll get really cloudy. So the water, dirty water, is like real cloudy looking. And so you would notice that it looks cloudy, but if you let it sit, all of that will settle down to the bottom and the top will be clear and the dirt will be basically like down in the very bottom. So it'll separate, but if you take and stir it up, it'll go cloudy again. You let it sit and everything settles out. That's a suspension. So the particles are large. They're not actually dissolved. They don't stay mixed unless you physically mix them. So other things that people oftentimes think about is a lot of oral liquid meds. And the ones that my kids used to love, which I always thought was very strange, is amoxicillin. Did any of you take the pink amoxicillin? That was like my children were so excited when they got like ear infections and stuff. We had to take amoxicillin, the pink liquid. Like it was the best thing ever. And I'm like, why? And they're like, it's delicious. And I was like, I don't know about all that. Because it like had this weird bubblegum, like artificial candy smell. I was like, this doesn't even smell good. But they were just like, oh yeah, this is delicious. Like if one got it, the other one would be jealous. They'd be like, well, I wish I had an ear infection. Like, no, I don't think you do. But one of the things that you have to make sure that you do is when you take it out of the refrigerator, you have to shake it. So it is a suspension. So the amoxicillin antibiotic is not soluble in water. So you shake it up to make sure that you evenly distribute the medication into the liquid before you dispense it. So that you're not just giving them the pink liquid part without the medication. It's helping to mix it. And they add like sugar to it and everything to kind of make it taste better and sweeter. And so then they enjoy it a little bit more. But yeah, so that's a good example. If you see that there's a medication that requires it shaken, it's because this is a suspension. Blood, on the other hand, and that's what this picture is, blood is actually all three. All three types of solutions are found in blood. This picture actually shows the suspension. So if I can zoom this, the only way that I'm going to be able to zoom this is I have to hold on to it. That's what I have found. Okay? So if I have to hold on to it with two hands. So blowing this up a little bit bigger. So you see the little container is the centrifuge, a lot like what we use when we spun down the bananas. So a centrifuge just spins, anything heavy gets pulled to the bottom. So in blood, the reason that blood is red is because there are red blood cells that are floating as a suspension in blood. So when you draw a sample of blood, it just looks like a red liquid. But if you centrifuge it, it would actually separate. If you let it sit, well, clotting happens. And so then it does separate as well. But in this one, and this is like the most anemic thing ever. I don't know if this is from a dog or from a cat, but in this, do you see that there is like this clear yellow liquid, and then there is this really dark liquid at the bottom? Normal blood, not that blood, normal blood. No, it's not going to let me do that. It hasn't done this in a while. Normal blood, about half of the tube is going to look like it is red, like dark red. About 40 to 45%, that's kind of a normal amount. So it would be about to here. So that's why I say, like, if you look at this, do you see where it looks like maybe 25% is red? All the rest of that is yellow. That's like a super anemic person or a super anemic animal, because it should be almost half and half. So this should all be red. The heavy red blood cells all go to the bottom of the tube when the centrifuge spins it. So those are all your red blood cells. They are microscopic cells that are not completely dissolved. They are constantly moving in the blood, and that's the reason why you can't see them when you draw blood. But if you centrifuge, you can actually do what's called a hematocrit, where you're actually measuring the amount, the volume of red blood cells that separate out by centrifuging. But this top part that's up here, notice that it's kind of yellow looking, kind of like a yellowish orange. This is the fluid of the blood. This is called what? It's called plasma. So this is plasma. So roughly, red blood cells usually make up about 45%. Plasma makes up about 55%. And then those white blood cells and platelets make up less than 1. And they actually collect right about here. So they collect at the layer where they're a little less dense than the red blood cells because they don't have iron in them. So they're right above. See that kind of orange little layer? So that layer kind of looks like this whitish kind of layer on top of the red. They call it the buffy coat. But that's actually where your white blood cells and platelets end up. So those are here. So red blood cells, white blood cells, and platelets, those are all solute particles that are suspended in plasma. And as long as your blood is moving, you cannot see them. But if blood is centrifuged, or if the blood stops moving, they will automatically begin to separate. So in this, the suspension, so your red blood cells, white blood cells, platelets, these are all suspended in the blood. And like I said, as long as the blood is moving, you'll never see them. But if blood stops moving, they'll all drop down, settle out. But the blood, plasma, actually has characteristics of being a colloid and being a true solution. This is because plasma has proteins. There are proteins in the blood that are dissolved in plasma. You can't see them, like colloids. Like you can't see the cream, or you can't see the fat in cream. You can't see the starch in gravy. You can't see the proteins in Jell-O. They're big, but they're dissolved. But they are the reason that plasma is thicker than water. These proteins are things like antibodies, clotting proteins, and proteins that help maintain water balance inside of the blood, which are called albumins. But what they do, they stay dissolved. Even if the blood stops moving, they stay dissolved, but they actually make the blood thick, that colloid characteristic. But then also dissolved in plasma are all of the very small solute particles that are transported. So what kinds of things are carried in your blood? Okay, well, oxygen is carried by red blood cells, but the other gas, which is so you have oxygen and carbon dioxide. Carbon dioxide dissolves in plasma, and it dissolves completely, and it's a small molecule, so it makes up a true solution. What else gets transported in your blood? Some people try to regulate it, try to keep it balanced. Sugar. So things like nutrients. So this would include like amino acids to build proteins, sugar, maintaining blood sugar, vitamins. So carbon dioxide, nutrients, and waste molecules. Waste molecules like urea, uric acid, things that need to go to the kidneys to get filtered out. Those are all carried, dissolved completely, do not separate out. They are all make blood a true solution. The proteins in the blood make blood a colloid, and the cells in the blood actually make blood a suspension. So blood is really like kind of like a combination of all of the different kinds of solutions just because of its nature. So when you dissolve a solute into the solvent, if it dissolves completely, and you could put more, they say that it's unsaturated. So most people make their coffee in unsaturated sugar solution because you just put like a teaspoon in. But if you put as much sugar in your coffee as would possibly dissolve, then you can make it what they call saturated. So unsaturated is less than the maximum amount of solute. So like your soda, it's got less than the maximum amount of sugar that can possibly fit in that liquid. But if we get to a maximum, they call that saturated. So this is the max amount of solute. Does anybody know of a substance where it's a saturated solution? It's the most that you can possibly put in. Honey. Honey is a saturated solution of fructose. So there can't be, you can't dissolve any more fructose in that. It's the saturated solution. And how thick is it? Super thick, right? It's a good example. In fact, there's so much sugar in honey, bacteria can't grow in it. So that's why you don't have to refrigerate honey. It can just sit on the shelf. Can you think of another one? I have one that I've had, a jar of this that I have had in my cabinet for probably 15 years. And I actually used a little bit of it at Christmas. It's another, yes, molasses. Do you have molasses at your house? No. Huh? Isn't it like ancient? It's grandma's. And it's like ancient. It's like literally, I was like, I was looking at the lid. I was like, well, the lid's not rusty, so I guess it's okay to use because I made molasses cookies at Christmas. But again, it's another one. Okay? A saturated solution, super thick. It has as much sugar dissolved in it as possible. It can't dissolve it anymore. That's a saturated solution. So think of honey. It is the max amount of sugar dissolved. If you add any more, like if I tried to add sugar to molasses, it would just be a crystal down in the bottom. You might remember when we did the soap lab, you actually had to use a saturated solution of sodium chloride in order to wash your soap after you made it. And so remember those bottles, they had like some crystals down in the bottom. You just took the liquid, but I made it by starting with water, and I just added salt and added salt and added salt and just kept shaking it, adding salt and shaking it until no more salt would dissolve. That's a saturated solution. So there's sort of like a picture. If I have just some, it's considered unsaturated. But when I get to the point, see that they're solid, you can see solid down in the bottom, then that's called a saturated solution. No more solute will dissolve. And it's like kind of like there's as many of those little solute particles dissolved as can possibly be put in. So there's a couple of things that we're not really going to talk about. They're kind of interesting things, but I don't have time if we're going to cover the rest of any of these chapters. So I thought, well, skipping Henry's Law, because we've already kind of talked about the respirations and everything else. So I think we're okay with that. We'll cover it a little bit when we talk about diffusion. So I figured we could leave that part off. So the next big part in chapter 8 is talking about like, well, how do some solutions dissolve and how are some different than others? So what they found is that there were some particles, specifically salts. Salts that dissolve in water typically form lots of ions. So if I take NaCl and I add water, so I'm just putting it in water and stirring it up, it will 100% form sodium ions, they're aqueous, and chloride ions, also aqueous. So what they found is these charged ions had the ability to carry an electric current. That's where the term electrolytes came in. So I know that you've heard of electrolytes like in terms of Gatorade, right? So you drink Gatorade to replace your electrolytes. It's really just saying your salts. It's talking about your sodium, magnesium, chloride. So the salts that are present in the body, Gatorade just contains a mixture of salts to try and replace what you might lose if you sweat a lot. Because when you sweat, you're going to lose those. So you may end up becoming dehydrated and you may end up with an electrolyte imbalance. Now, other molecules that also dissolve in water, they don't always break into ions like sodium chloride does. So sugar is a good example. So sugar, glucose or sucrose, any of the sugars, they're covalent molecules and they're polar. So they do dissolve in water. But when they dissolve in water, they don't form an ion. So they called them non-electrolyte. So an electrolyte forms ions. Non-electrolytes don't. Even though they dissolve in water, they can't carry an electric current. Then they found this really interesting group of salts or ion-forming compounds that form ions a little bit. So they don't form lots of them. They actually just form some, but the majority of the solutes actually remain undissociated or non-ionic. So this one, the one example here, is actually acetic acid. Acetic acid, its common name is vinegar. So I brought my little demo to show you. It's my demonstration. I have this, not OSHA approved. So I have a light bulb apparatus. Okay, so there's a light bulb, and here's the two electrodes. So when I plug this in, the only thing stopping the light bulb from lighting up is those two electrodes don't touch. But if I can carry electricity from one side to the other, that will complete the circuit and the light bulb will turn on. Okay, so I've like never electrocuted myself. And hopefully, I've only got a couple more semesters, but I don't want to do that. So first off, this is just water. So this one I'm going to use as my rinse. So notice if I just take water, just plain water, and dip the electrodes in, nothing happens. Okay, so that's the one. I'm going to put it over here so that I rinse in between. All the rest of these are just distilled water. So I can show you again. This one's just distilled water. And so when I do the dip, nothing happens. But now I'm going to take some sodium chloride. So this is just regular table salt. I'm just going to put, you don't have to put very much in. Just going to put a little bit in. And we'll stir it. I want the salt to dissolve because what's happening when the salt dissolves, I'm getting sodium ions and chloride ions that are forming. And now, when I put this up, okay, I have a bright light bulb. So this is called a strong electrolyte because in water, it forms lots of ions, typically like 100% ions, and it can carry the electric current strong. So I'm going to leave it next to that so I don't get them all mixed up. I'm going to rinse just to make sure that there's no extra salt. But now, I also brought sugar. Okay, so this is dextrose, which is just glucose. So if I put a splash of that in here, right, so same, tried to put about the same amount of glucose as I did with the sodium. And again, I'm just trying to mix it up. I want to give it time, make sure that it completely dissolves. And so just like table sugar, glucose dissolves very well. It's polar, so it dissolves really well in water, so you can't really see it anymore. Okay? But this one, because it does not form electrolytes, I don't see any change. No light bulb, because sugar is covalent. It doesn't form ions, so it can't carry the electric current from one little pole to the next. So that one here. So the third one. So the third example is acetic acid. So I have a jug of vinegar, and you can like totally smell it as soon as I start pouring. I'm going to add it to water just so that I'm mixing it just like I did with all of the other ones. This one, when I put it in, see the difference? So see how it's like dim compared to the sodium chloride? So it only lights that light bulb up sort of a little bit rather than having this normal brightness. And that is because a lot of the vinegar molecules stay together. They don't form ions. Just a couple of them do. So it can carry an electric current, but it doesn't carry very much. So that's where it got that name of being a weak electrolyte. So then came the fun part. I was like, okay, well, what else can I do? Okay, so I have ethanol. So you tell me, ethanol, CH3, CH2OH. Do you think it's going to be an electrolyte, a non-electrolyte, or a weak? Strong, weak, non. Non, okay. All right, so I'm just going to pour it. And I'll add some water to it as well. I'm going to put it over here on the next one. Just like I added water to everything else, we'll add some water to this and stir it up. So this is ethanol. And this one is non. Okay, so ethanol is entirely covalent. Ethanol does not form ions. So you notice that there's no light bulb, no light that goes on, not even dim. So that's a non-electrolyte. We'll rinse. So what about hydrochloric acid? HCl. So I brought some hydrochloric acid. We're actually using it tonight. We're doing an acid and base lab tonight in lab. So I was like, well, I'll take this one too. All right, I'm going to put some in water. What do you think? Strong, weak, or non? Weak? Strong? What do you think? Strong? Okay. So I think it's this one. Yeah. Very strong. So this way, you know that these, remember when I told you about like being careful with them? I was like, these are really corrosive. They make lots of ions. And when you have acid ions, they're very reactive. So they cause damage to the skin, damage to body tissues. So that one's a really bright one. Okay. So that one's hydrochloric. And so the last one. So then I was like, can't find a weak. So I got online and they said one of the ones that you can try is calcium hydroxide. And so I was like looking in the stock room, and I bet this bottle of calcium hydroxide is as old as I am. It's like food grade. I'm like, food grade? Who eats calcium hydroxide? So I was just like, sure, we'll try that. So I'm just going to try and get like about the same amount of what, like the acid and the base that I put in. All right, so it looks about like the same. About the same. I'm going to stir it. We'll just see how bright it gets. So it was touted as being a weak electrolyte. It's kind of cloudy. And this one, yeah, kind of like in the moving it up and down and stuff. It's a lot more like the vinegar. I'd say it's a little bit brighter than the vinegar, but it still kind of goes back and forth, whereas the salt and the acid, sodium chloride and the acid, like that light bulb stayed lit no matter what, stayed lit the entire time. So this one, what it means is that calcium hydroxide doesn't split into ions 100%, only some of them. And so that's why it's a weak electrolyte, because it can't carry very much. Another successful demo. Did it? I'll execute myself. It's never the goal.
I was curious, so I just Googled it, and food grade calcium hydroxide is used to make authentic corn tortillas.
Oh. That's what it's for then. Like legit, like I was like, ooh. This is like in the very back little corner on the shelf. I was like, let's just take this and try it. I wonder what they don't sell it as calcium hydroxide. What do they sell it as? Is it like, I was wondering if it was something that they would use in making like hominy, which is like when you take,
It's, when you soak the corn in calcium hydroxide, it significantly increases the bioavailability of niacin, which helps to make the corn easier to digest. And it's used in similar fashion when making hominy goods.
Oh yeah, that's what I was thinking was hominy when I just hearing that. But what did they didn't give you a common name for calcium hydroxide?
Pickling lime?
Pickling lime?
Pickling lime.
Yeah, so maybe that would be it then.
So it's in your pickles too.
To help break them down or help like to think about like so because it is a base, but it's not a strong base. So it's sort of like a weak base, just like acetic acid is an acid, but it's not a strong acid. Like vinegar, you like eat vinegar, but you wouldn't eat hydrochloric acid because it's a strong acid and it's much more reactive to body tissues. So let's do a couple of them just as for examples. Here's how you would write a reaction for a strong electrolyte. Okay, so when you do this, you always start off with the compound. It's always going to be a compound of some sort. So the compound's written first and then an arrow. And so they'll put the water above or below just to show that you're dissolving it. So you're not really reacting it with water. You're just putting it in water. Notice that the arrow goes from right to left. Okay, if it's a strong electrolyte, the arrow goes completely from right to left. You can put the little H2O above or below, doesn't matter. But then 2, on the product side, they're both aqueous. You have to split them 3. The products have to have a charge. So remember, you can figure out their charge by looking at the periodic table. So see, like magnesium's in group 2, so it's a +2. Calcium's over in group 7, it's a -1. So remember how you got the charges for those? And now the other thing to do is that the products would always have the total number of each of the atoms on each side have to balance. So notice in this one, I had to put a 2 Cl-. because the formula is MgCl2. So there's 2 chlorines in MgCl2, so that means I end up with 2 chloride ions. So it's a pretty simple balancing, but you should still balance them. Okay? So a strong electrolyte, arrow goes left to right only, because it's going to be 100%. Always the products, then like this one should be AQ. They didn't put it in. The product should be aqueous. And then make sure that the products are listed as ions and they should balance. Now, if I have a non-electrolyte, these are the easiest ones to recognize. So the arrow, same thing. The arrow goes left to right, and you can have the water above or below. It doesn't matter. So that's like a strong electrolyte. The product is written with AQ, just like a strong electrolyte, but there's no ions. So notice the products do not get split. The product is the exact same formula as the reactant. So see in this one, C6H12O6, this is glucose. When I put glucose in water, it dissolved. It became aqueous, but it doesn't change. It stays as one thing. So the product formula does not change. And it's always going to be balanced because it'll always be 1 and 1. So 1 molecule of glucose dissolves into water, and there's one molecule of glucose aqueous. So really, they say the only difference between the reactant and the product is one goes from a solid to an aqueous. So it goes the phase, what state it's in, solid to aqueous. And you never have to worry about balancing it because it's always balanced. Now the weak. So the weak electrolyte, what do you notice about the arrow? Both directions, okay? So strong and non-electrolytes, the arrow goes one direction. Weak electrolyte, the arrow goes in both directions. So that's one way you can recognize a weak electrolyte. If you see the arrow going both directions, then you know it's a weak electrolyte. The products are still aqueous. So that's the same. All of them end up aqueous as the product. But in this, like the strong electrolyte, weak electrolytes do form ions. And if they're not already balanced, you will have to be able to balance them. Most of these ones are balanced though, because when they dissociate, it's only one positive charge, one negative charge. So I will tell you, weak electrolytes typically only form about 1 to 5% ions. So 95 to 99% of the molecules stay like the reactant. So like 95% is this, only 5% form those ions. So when they say it's a weak electrolyte, it's really weak. Like it really doesn't make a lot of ions. It's not like a 50-50. Most weak electrolytes form just a little bit. And that's why it really doesn't have enough electrolytes to be able to power the light bulb. So let's practice a couple of them. So the first 2, strong electrolytes. Second 2, weak electrolytes. Last 2, non-electrolytes. So see if you can finish these. follow the steps. I can smell his vinegar now.
The second one is that +3 and -2.
Mm-hmm. Because remember, if you reverse the formula, that would tell you the charge. All right. So in the first one, what did you do? You split HCl into H with a plus, and it's aqueous, and Cl with a negative, aqueous. And this one's already balanced, so you don't have to balance it, right? So it's already like a 1-in-1. One hydrogen on each side, one chlorine on each side. So then what did you have to do with Fe2O3? So you put Fe and its charge with the +3 AQ And then O has a -2, because remember it's over in group 6. So it's a -2, aqueous. But in this one, I have to balance. So what do I have to put in front of the Fe? How many Fe's do I need based on the reactant? So if I have Fe2 over on the reactant side, that means that I have to have 2 Fe's on the product side, and then oxygen would get a 3. Okay, so see the formula on the reactant side, Fe2 means 2 irons. So on the product side, I got to put that 2 in front of the iron. O3 on the reactant side means I got to put 3 in front of the O. Okay, but that's it. And like I said, so pretty much all you'll ever have to do is change the product side with those in balancing. Whatever the number in the formula on the reactant side, that tells you how many of each of those you'll have on the product side. Now, if I have a weak electrolyte, the same thing happens. You do it exactly the same, just put the double arrow. That's really the only difference. I'm still going to separate them into ions. So Na2CO3, what would that form when it splits into ions? Na, right? Because that's the metal. And Na has a, what charge? Positive charge. So that would be AQ. Plus CO3, remember the carbonate 2-, which would have an AQ. What would I need to do to balance it? How many sodiums would I need? Look at the formula on the reactant side, 2. So Na2 means I have to have 2 sodium ions. So that number in the formula tells you how many. But CO3, I only need 1 of those because there's only 1 CO3 in Na2CO3. So there's only 1 CO3, the carbonate ion, in the formula on the reactant side. So I only need 1 CO3 on the product side. What about HF, hydrogen fluoride? It would split into hydrogen, H+, and that would be aqueous, and F, which has what charge? It's a negative, because it's over in group 7, right? So remember, like chlorine, it would have a negative charge. You got to add the aqueous. What about numbers? How many hydrogen, how many fluorine on the product side? 1 of each, because the formula is just HF. So that means there's only 1 hydrogen, 1 fluorine on the reactant side, so I'd only need 1 hydrogen, 1 fluorine on the product side. It's just kind of like HCl. HCl would have been the same, 1, 1, and 1. Just look at the reactant, the formula on the reactant. Just make sure you put to balance the product side. Non-electrolytes are super easy though, because non-electrolytes, the arrow goes from left to right. There's no ions, so you just list the reactant exactly the way it's written. So CH3CH2OH becomes CH3CH2OH. You just change L from liquid to what? AQ. You don't have to worry about balancing it because there's no change in the molecule. All it's saying is that it dissolves. So that is ethanol. So I did that one as an example. So the ethanol dissolved, but it doesn't form ions, so it's a non-electrolyte. And then the last one is table sugar, C12H22O11, so it's sucrose. Added it to water, stir it up, completely dissolves. But when I try to light the light bulb, nothing happens. So that means this exists as C12H22O11. But instead of being a solid, it's now aqueous. So the only thing that changes is the AQ part. So you can tell a strong electrolyte because the arrow goes left to right and you make ions. You can tell a weak electrolyte because the arrows go both directions and you have ions. And you can tell a non-electrolyte because the arrow goes one direction and there's no ions, right? So those are like being able to pick them out. So if I gave them to you, so if I gave you like this on the exam, if I gave you that reaction, could you identify if it's a weak, strong, or non-electrolyte? So just go based on those criteria and you shouldn't have any problems.
On it says if we forget to put the AQ, is that like a point?
So really, you're not going to have to finish these reactions. It's really picking it out, okay? So like I said, if you look at a reaction and you see the arrow goes in one direction, then you know it can't be a weak electrolyte. Then it's got to be one of the others. So if there's ions, it's a strong electrolyte. If there's no ions, it's a non-electrolyte. If I ask you the question and I have the arrow going both directions, then you automatically know it's a weak electrolyte. Okay, so those are sort of how they're different, just because it's whether they make ions 100%, a little bit, or not at all. Okay. All right, so there's also the equivalents in ions, but like I said, there's some things that we're just really not going to talk about in these chapters, just to try and get through like the bulk of it, but not necessarily all the nitty-gritty details. I encourage you to go through and read them, but there won't be any questions on those. Concentration is this whole middle part. So this, again, this is a math thing. So when we think about a solution, you're talking about stuff that's dissolved. And so that is now the concentration of a mixture. So there's a couple of different ways that we're going to talk about them. We're going to talk about percent solutions. So percent, remember percent is out of 100. So when you're talking about a percent of anything, it's based on 100 as the whole. We're also going to talk about what is known as molarity. So molarity is talking about how much of a solute is in a solution, but it's based on moles. So remember we talked about moles way back in chapter 3, so we'll have to do a little reviewing for that. The third way we're going to talk about concentrations is what happens when you have really, really small concentrations. And so in that, you may need to talk about how much out of 1,000,000 parts per million. So that's like 1 part per million pieces, or even parts per billion. So that's an even smaller amount of solute, but can actually be very important when talking about some toxins. So those are really kind of like the 3 things that we're going to cover. So the first one, I thought it was percent, but it's not. The first one is molarity. So this is a very common concentration that's used in chemistry. Most of your solutions are in terms of molarity. And so molarity is defined as being how many moles of your solute is dissolved per liter of solution. So now remember what the mole is. Remember that the mole is equal to the formula mass of any substance. So you'll need a periodic table and a calculator. How many? Two. Got him? Okay, good. I thought about bringing him out, taking him out, but I forgot. I will need one. Okay, so remember, if you're looking at whatever the formula is of a substance, the formula mass is just the mass of each of the atoms in the formula. So if I wanted to know how many grams in 1 mole of sodium chloride, I would just look at how many What is the mass of one sodium? What is the mass of one chlorine? Add them together, right? And so remember, mass is the number with the decimal places on the periodic table. That's the atomic mass. The number underneath, just round to the nearest whole number. Don't worry about keeping the decimal places, just round those. So if I wanted to know what 1 mole of NaCl is, I would just look at sodium. So sodium is 22.9, so I'd round that to 23. And then I look at chlorine. Chlorine is 35.45, but I round that down to 35, and I just add those two together. Okay, so that's 58 grams is what would be in 1 mole of sodium chloride. So it doesn't matter what the solute is. It could be ethanol, it could be a sugar, it could be anything. It could even be some kind of weird, large, humongous, like caffeine molecule where you have like 30 carbons and 25 hydrogens. You just would multiply the number of atoms times their mass, do it for each one, and just add them up. So that's the formula mass. Now, it's always going to be in a solution, right? Because this is what we're talking about, is solution. So you know that there's always going to be dissolved in water. So the entire volume of the solution, if we're talking about this molar or molarity, they use this capital M, and that's referring to how many moles per liter. If I know the concentration in molarity, and I know the volume, concentration times volume can tell you the amount of solute. So in lab, remember in lab we made soap, and we mixed a fat or an oil with 40 milliliters of 6 molar sodium hydroxide. So the first question says, okay, well, how many moles of sodium hydroxide is this? So the first thing that you want to do is you want to take the concentration and change it to what it means. Just like percent, remember we did this in lab too? I said if you have like 10%, just change that to 10 grams per 100 mils. Don't leave it as percent, because percent doesn't have a unit. Percent is sort of a concentration. And so in this one, I want to take 6 capital M, NaCl, and change it to what that capital M means. That means 6 moles per 1 liter. So capital M is moles per liter. So now I have units. So if I have units, now I can multiply or divide to get my units to cancel, because this first question is saying, well, how many moles? So if I can multiply 6 moles per liter times the amount in liters, then liters and liters will cancel, and it would give me my answer in moles. So concentration times volume will tell you the amount of your solute. So 40 milliliters. So I can't multiply 6 moles per liter times 40 milliliters because my units are not the same. So I have to convert this to liters. So this is just a single unit conversion. Remember, in the unit conversion, what unit would I put on the bottom? Milliliters on the bottom, liters on the top. Milli means 1,000. Liters always gets the 1, right? Remember, so the liters is that base unit. So when I do this math, 40 divided by 1,000 would be 0.04 liters. I can multiply that times my concentration. So 6 moles per liter times 0.04 liters. Liters and liters will cancel, and it's going to give me my answer in moles. So this is concentration times volume will tell me the amount of my solute. So this is 0.24 moles of sodium hydroxide. So that's this answer. How many moles of sodium hydroxide? If I know moles, I can figure out how many grams that is. So if I want to do moles to grams, I have to figure out the formula mass. So you got to look at your periodic table. Sodium, we said, is 23. Oxygen is 16. And hydrogen is 1. So if I add those all up, I get 40. So there's 40 grams is equal to 1 mole. So that's the formula mass. You just add up the mass of sodium, oxygen, and hydrogen. That's sodium hydroxide. There's 40 grams in 1 mole. And remember that you use this as a unit conversion. So if I have 0.24 moles, I'm going to put moles on the bottom. The answer I want is grams. Grams goes on top. Grams gets the 40. Moles gets the 1. So 0.24 times 40 is 9.6 grams. Now in this, if I was going to go with significant figures, yes, I would round this to 10, because 6 molar, that's 1 significant figure. 40, 1 significant figure in my problem. So I would end up rounding this. So this would end up rounding to 10 grams. Because there's 1 significant figure here, 1 significant figure there. So if you see that capital M and you're given a volume, just change that capital M to moles per 1 liter, multiply it times the volume, and that'll tell you how many moles of your sample. If they need to find mass, then you have to use the formula mass to go 1 step further. 10 grams. So, yeah, that's 1 significant figure in 10. Just the 1 is significant, right? So 9.6 is 2 significant figures, but if I look at my numbers in my problem, 40 is only 1 significant figure, 6 is only 1, so I would take 9.6 and round it to 10. And so I'd call it 10 grams. So here's this one. So 88 grams of sodium chloride is mixed in water to make a final volume of 0.75 liters. What is the molar concentration? So here, I know the amount of my solute. So I need to convert that to moles of my solute. And if I want to figure out the molar concentration, I will then divide it by my volume. And that will give me moles per liter, which is molarity, or molar. So the amount of my solute is 88 grams. I need to convert it to moles. So that means I'm going to have to put grams on the bottom, moles on the top. Sodium weighs 23. The chlorine we said is 35. So I'm just going to add those together. So that's 58 grams is equal to 1 mole. So that's what I'm going to use to convert. So I put 58 on the bottom. Moles gets the 1. Because there's 58 grams per 1 mole. (88) divided by 58 You get all these numbers. 1.517241379 moles. Like that's everything on the calculator. But I don't want to round this because this is not my final answer. Because now if I take the number of moles and divide it by the volume that I have, and there's the volume, and it's in liters, so I'm all set. So I just take this number and divide it by 0.75 liters. That'll give me an answer of moles per liter, which is what my molar value is. So in doing the math, I got 2.022988506. So now instead of just saying moles per liter, I can use that capital M. That's the molar concentration. That capital M is saying the same thing as moles per liter. It's telling me how many moles of sodium chloride is dissolved per liter of solution. I can't keep all of these. So go back to the number. So when I look at the number, 88 is how many? 2. 0.75 is 2. So I can keep the 2 and the 0. So I would end up rounding this to 2.0 capital M NaCl. That capital M means moles per liter. So in this one, here's sort of the steps. If you're given the amount of the solute and you want to know molarity, you convert to moles and divide it by the volume. If you're given molarity and you want to know the amount of your solute, you're kind of going the opposite direction. So you just take the molar concentration times the volume, then convert it to grams. So I think there's another one. Yeah. So this one, I'm giving you the formula mass of glucose because it's 180. So it's C6H12O6. So if you added all those up, you get 180. So if you were going to calculate the number of grams in 1 mole, that's how you would do it. So glucose is 6 carbons, 12 hydrogens, 6 oxygens. So I'd have to take 6 carbons times 12, which is the mass of each carbon. So that'd be 72. 12 hydrogens, the mass of each one is 1. So that'd be 12. And then 6 oxygens, and each oxygen weighs 16. So that'd be 96. So if I add all of those up, you should get 180. So that's where that 180 comes from. Add those ones up. That tells me that there's 180 grams in 1 mole. Or how many grams per mole. It's called the formula mass. Just add the mass of each of the atoms in the formula. So when you see that capital M, first thing you want to do is convert that, change it back to a unit number. So 0.65 big M glucose means what? Moles per liter. So just change that to a unit, because once you get the unit, now you can use it. So the capital M is like the percent sign. It doesn't really have a unit value, so just change it back to what it represents. So this is my concentration. So what do I multiply it by? Concentration times volume. So where's my volume? 3 liters. So you see that liters and liters will cancel in the multiplication. So 0.65 times 3.0. That'll tell me how much of my solute, the number of moles of my solute. I got 1.95. 0.65 times 3. So the last is how many grams. So once you get moles, now I can just do one more step to convert it to grams. So if I have 1.95 moles, 1.95 moles of glucose times in a line. What unit do I put on the bottom? Moles goes on the bottom because whatever you're given, right, that's what goes on the bottom. And then we said grams goes on the top. There is 180 grams in 1 mole. So that's just the formula mass. So I'm just going to multiply the number of moles times the formula mass. Moles and moles will cancel this way. Times 180. And I get 351 grams of glucose. It's a lot of glucose. Can I keep all those numbers? Why? How many in 3.0? 2, because it's a 0 after a decimal. So remember, that's 2 significant figures. 0.65 is 2. So that means I can keep the 3 and the 5. So that 1 becomes what? A 0. So it's 350. So there's 2 significant figures in that answer. Next time we'll practice a couple more of these because I know like just making sure that you can set them up straight. So there's like another one there. But then we're going to do percent because percent is really very similar. You just have to change the term percent to what it actually means, just like you change molar to what it means. Percent, you don't have to work with moles. It's all just grams. So it sort of like takes out the whole molar part to it. And then we'll go on and do the parts per million and parts per billion. So that'll be the last one. Okay? So you will see in lab tonight, if you're coming to lab tonight, you will